Hello, Allegheny College Introductory Astronomy students. Welcome to another astronomy lecture brought to you by Bella and me, Jamie Lombardi. I hope you're all doing well and staying safe. Today's lecture that we're recording is for Monday, April 6th, and it will be mostly about our galaxy, although at the beginning of class today we'll have a few things to say about the search for gravitational radiation, finishing up material from chapter 14. Last week we were talking about things like black holes and so on. One of the most beautiful things that have occurred in astrophysics in recent years is that we now have working gravitational wave detectors. We thought last week about how if you have a mass and you imagine putting it on a sheet, the sheet would become deformed, and that was an analogy for how in general relativity energy deforms space-time and then things move in response to that curved space-time. Well, imagine that you had two ball bearings on one of those rubber sheets that were orbiting around one another. And these ball bearings you could think of as representing black holes, say. What happens is that if you imagined making two little pen marks out on the sheet far away from the black holes, you would see those pen marks get the distance between them get stretched and compressed and stretched and compressed in sync with the orbiting black holes. And so what that is really is perturbations in the space-time that propagate outward from the black holes. This is representing gravitational waves. And so gravitational waves are a prediction of general relativity from Einstein. And starting with the Hulse-Taylor pulsar, which were two neutron stars that orbited around one another, we saw that their energy loss from gravity waves explained their in-spiral rate. So as energy drains out of that binary, in the case of Hulse-Taylor, it was two neutron stars. Here, more generally, in the cases that I'm speaking about, it might be other objects like black holes. But in any case, the energy loss causes the orbit to shrink, and the two objects orbit faster and faster and faster over time. Now, LIGO is a collaboration that has been set up for almost 30 years now. But it's only been in the last 5 years that they made their first detection. LIGO stands for Laser Interferometer Gravitational Wave Observatory. And here is the one in Livingston, Louisiana. Notice these two long arms that we'll talk a little bit about. Here's the one in Hanford, Washington, in the eastern portion of Washington. And these arms are kilometers long. And so what happens here is that a laser light is bouncing back and forth between mirrors on the ends of these arms. And what an interferometer in general works under the principle is that if these laser lights that are bouncing back and forth experience a different path length. Why would it experience a different path length? Let's say one of these gravity waves from two merging black holes far away, maybe in another galaxy. They pass by and through our Earth, and they stretch and compress, and they stretch and compress the distance along one or both of these arms. And as a result, the laser beam has a different distance to travel. And had there been no gravity wave, maybe these two laser beams at a certain point on a screen when they're recombined would be in sync with one another, and so you would get a nice bright spot there. Or in another part on the screen, maybe the two laser beams would be half of a phase out of sync with one another, and so you would get a dark spot right there. But as soon as you start changing the length of the arms, then the pattern that you have, the interference pattern on that screen, is going to change as well. And so we can detect, LIGO scientists detect the passage of gravitational waves by this interferometry technique. We have in our building a LIGO scientist. He works for and is paid for by Louisiana State University. His name is Alex Urban, but he is a graduate of Allegheny College. His office is just down the hall from the planetarium because he's working this year remotely for LIGO. And he was on site Well, he was in the state of Louisiana, back at his apartment, when the first detection of a black hole came in back in 2015. And he went into work that day, and it was just a day of excitement and joy. Because if you think about it, think about how astronomy changed 400 years ago when Galileo Galilei first used a telescope to look at the sky, right? The whole universe opened up to humanity. And since then, how has astronomy been done? Well, with rare exception, what people do is they are looking at light that's coming from space. Sure, we might collect moon rocks and meteorites and do other related things, but for the most part, astronomy has been looking at light coming from space. And now we have a different kind of radiation, this gravitational radiation that we're capable of detecting from other sources. And so this gives us a whole new lens, if you will, a whole new way to look at our universe. These detectors, these LIGO and other related gravitational wave detectors, are remarkably sensitive. If you take this Hanford site, for example, which is on the eastern side of the state of Washington in a desert, isolated from many people and activities, because any little activity can be picked up. So, for example, the water as it flows in onto the shoreline on the west coast of the United States, that beating of the water, that can be felt and detected by these interferometers, right? So you can't have lots of cars driving around and so forth. Trains that pass by dozens of miles away from the Livingston site is picked up by this detector. So there's lots and lots of noise out there that these detectors can detect and do detect. But because we know what the gravitational wave signal looks like for merging objects, that can be predicted, and you have a template, then you can try to look for that needle in a haystack, so to speak, to look for that little signal that just sticks above the noise. So merging black holes, as I was mentioning, they will, as they're orbiting, orbit faster and faster and faster. As they lose energy to gravitational waves, their orbit shrinks. And so as they go faster and faster and faster, they can start to orbit at frequencies that are comparable to what the human ear can detect. So hundreds of hertz. Remember, a hertz is a cycle per second. So what I'm saying is that the black holes would orbit around one another hundreds of times per second in their final orbits before they merge together. And so here's a nice YouTube video that was put forth by Cosmo Knowledge, and it uses actual data from the LIGO and MIT sites. This first visualization that you're seeing here, these are not observed data of black holes merging, but rather it shows you what it would look like if you could see this up close and personal. And one thing to note is that there's a lot of deformation in the vicinity of the black holes. And that has to do with the fact that the light paths are gravitationally lensed. You have these stars that are far away on the far side, back beyond the black holes. And light from them is coming, but as it passes the black holes, it'll be bent due to that curvature of space-time. And so that lensing is going to be very dynamic here as the two black holes orbit one another. And so here we're looking at two black holes, each with about roughly 30 times the mass of our sun. And you can get a feel for how the light around it would work. Now, these data here are showing you in a cross-sectional slice what the gravitational radiation would be like. So as the two black holes orbit around one another, gravity waves are emitted as a result. You can see that here in this visualization. And so you can appreciate a little better the merging then of the black holes and what that would look like in space-time if you could see that curvature. Remember, what that curvature is going to be representing is perturbations in distances between two neighboring points in space. Now, what's great about having multiple detectors, one in Hanford, one in Livingston, and there's also the Virgo European Gravitational Wave Observatory, is that you can be more confident that a signal you detect is a real signal if more than one of these observatories detects it. Not only that, gravity waves travel at the speed of light. And so if Hanford detects the signal and then a small fraction of a second later Livingston detects the signal, then you can start to tell where in the sky the source might be from. The more observatories that you have detecting the signal, the better determination you're going to be able to make about where that source was. If you just had a single detector, you wouldn't really know where the signal came from. But the more detectors you have, the better idea you could get. Because if the signal hits Hanford first and then Livingston second, the source of the signal must have been closer to Hanford. It must have been on the side of the Hanford's side of the Earth, and the signal was coming then through Hanford and onward to Livingston. So here, let's go ahead and take a look at what LIGO Observatory received. Now, of course, they're looking at strains in the arm lengths. They're looking at deviations in the arm lengths here. They're not actually detecting a sound, but this has been converted to audio so that we could appreciate it. If you look at the vertical axis here, you see it spans from tens of hertz up to 500 hertz. That's cycles per second. And so here, first we'll play this at the regular rate. So what happened there was that they played through the signal twice at the regular rate, the last half second before the black holes merged, and then they played it through at an enhanced speed so that you could hear it a little bit better. It brought the frequency up into the range which is more easily heard by the human ear. Now I'll raise the volume here and see if we can't hear that again. So that's the regular rate right there. And I'll pause this here because let's see what we're looking at. If you look here on the vertical axis, that's hertz. Here on the horizontal axis is time. You see these data right here that go do higher and higher hertz? That's because the black holes are orbiting faster and faster and faster and faster as they plunge in toward one another ultimately and merge together. And notice that the same kind of signal was detected in Hanford as in Livingston. This graph here is what's called the strain. And the prediction for the strain matched beautifully well to this experimental data. And it showed us that because we knew what a black hole merger event should look like, with great statistical confidence, we could say that the data we were looking at here was from the merger of two black holes. So we'll play it through again. I've bumped up the volume a little bit, and you may be able to hear this chirp. It comes in a background of noise, so you've got to listen carefully. You hear that whoop, whoop? That's the chirp that we're talking about that signals the merger of these two black holes. At one point, a few years ago, I guess it was back in 2016, once they announced the 2015 detection, that chirp was my ringtone on my phone. So here we get another look at those gravity waves that we're thinking about. And so you see the two black holes orbiting around one another. The gravity waves are coming out, taking away energy from the particular binary system, and then causing those two black holes ultimately to merge. So I'd encourage you to, subscribe to Cosmo Knowledge there, who took and put together some of these data from the Caltech, MIT, and LIGO laboratories to make that interesting YouTube video. All right, so since that detection back in 2015, there have been more and more of these black hole merger cases that have been detected. Here, in fact, even on the same graph, we see a neutron star merger case that's been detected. These combine data from LIGO and Virgo. And so you can see here that most of the black hole mergers that have been detected are sort of like the one we were just discussing. Two black holes of approximately 30 masses. So for example, in this case, this one had about 20 solar masses. This one was a little bit more than 20. So altogether, before the merger, we're talking about more than 50 solar masses. After the merger, it was actually less than 50 solar masses. What happens here is mass is destroyed in the process. Energy is released in this final burst of gravitational radiation. And in the loss of that energy, you have destroyed mass from the black hole. So the black hole, or the merged object you make, doesn't have a mass, does not have a mass. That is simply the sum of the two masses of the objects that formed it. The dots here that don't have any arrows connecting them, those are black holes whose masses have been determined by other means, by looking at the accretion disks around them, for example. And so there are a lot of these so-called stellar mass black holes that are known to exist. Down here in the 1 to 2 solar mass range, there are a lot of known neutron stars. And then there is this mass gap in between. It'll be interesting to see if anyone ever discovers a black hole that has a mass in this mass gap. All right, so that's it for chapter 14. We're now going to move on to chapter 15, talk about our galaxy. And what we're starting out with here is an all-sky view of our galaxy in the visible. So if you look carefully, you'll see that there's an oval here. And that oval is the edge of our picture. But the entire sky has been imaged and then flattened out and placed inside of this oval. At the center of the oval is the direction towards the center of our galaxy. And along this long axis of the oval, that is the plane of our Milky Way galaxy. And so as you go upward, it's like you're tilting your head higher and higher away from the direction towards the center, or as you go downward here, you're looking lower and lower. But this point on the far left is the same point in the sky as this point on the far right. And that would be the point directly behind you. And so here we're looking at the entirety of the sky. And you can see things like the large and small Magellanic clouds, the disk of the galaxy, the dusty gas lanes that exist within that disk. So those dusty gas clouds, they are obscuring our view, at least in the visible light, of the center of the galaxy. Can't really see what's going on there because the dust is just too opaque. These dusty gas clouds are what we call the interstellar medium, the medium between the stars. And it's out of those it's out of those gas clouds that you have star-forming systems. There is the environment where stars form. So we can learn a lot by looking at our galaxy in different wavelengths. So for example, if you look in the radio at the 21 centimeter wavelength, and 21 centimeters is a special wavelength. It corresponds to when an electron in the ground state of hydrogen goes through a spin flip. And so that releases a very long wavelength light, 21 centimeters, right? About the same length as the width of a sheet of standard piece of paper. And if you're seeing 21 centimeter emission, it's coming from those spin flipping electrons, and so we're talking about hydrogen gas. So by looking in the 21 centimeter wavelength band, we can see where the hydrogen is in the galaxy, and it exists, not surprisingly, along the disk. In the radio as well, but now at a different wavelength, we could look for lines from carbon monoxide. And carbon monoxide is a molecule. It's C and O together. And so
in order to have molecules in your gas clouds, it's got to be cold. If it were any warmer, then the molecules would smack one another and break up into individual C's and O's. But in these molecular clouds, you can have carbon monoxide. And so here we're tracing out where you have these colder molecular clouds. In the infrared, you can tell where there's a lot of interstellar dust because it heats up to maybe hundreds of Kelvin by surrounding radiation and then glows in the infrared. And so here we can see that infrared dust. In a little bit nearer infrared wavelengths, that is shorter wavelength, larger frequencies, there the light can actually pass through the gas clouds, and it allows us to see down towards the center of the galaxy, for example. Look at it in the visible. There our view was obscured. In the near infrared, now we can see down to the center of the galaxy. In the X-ray, we can see where there are hot bubbles of gas. A lot of these bright spots in the X-ray image are corresponding to individual binaries. Maybe you have a compact object of a neutron star or a black hole, for example, with material that's forming an accretion disk around it and getting very hot and emitting in the X-ray. You can see individual objects like that here in this all-sky X-ray view. And then in the gamma ray, we can look at collisions of cosmic rays with atomic nuclei in interstellar clouds. So here's yet another way of seeing where the gas clouds are within our galaxy. So we can learn a lot about the distribution of matter within our galaxy by looking at it at all these different wavelengths. And what our structure of the galaxy looks like is this. It's nice and flat in one axis, and then it's axisymmetric as you look at it along another direction. So here, it's about 1,000 light years thick, this disk, even though it's about 100,000 light years across from end to end. Our sun and the solar system are 28,000 light years away from the center of the galaxy. Now remember, a light year is the distance that light travels in a year. It's about 10 trillion kilometers, or roughly 6 trillion miles. And so it's a gigantic amount of distance. It would take 28,000 years for light to travel from the center of the galaxy to us. When we look at images of the center of the galaxy, we're seeing what happened there 28,000 years ago when that light had left. Now, from the top, you see these arms that come out. The sun is in one of these so-called spiral arms that come out from the center. And in the center, you have this bulge of stars. Here, this visualization will allow us to take a look at our galaxy from many different angles. There, as we look at it more and more edge on, you can appreciate how flat it is. Now, around the galaxy, in a nearly spherical distribution, we have the halo and the stars within the halo. Those stars include globular clusters of stars, for example. And so that is how matter is distributed within our galaxy. Of course, these are drawings of our galaxy because it's not technologically feasible to ever launch a spacecraft that's going to exit the galaxy and then turn around and take a picture and then beam the image back to Earth, right? Look at the kinds of distances that we're talking about here. Tens of thousands of light years that first would have to be traveled, and then you would have to send a signal back over those large distances. Now, how are stars orbiting and moving in our galaxy? Well, it depends whether we're talking about stars that are in the disk or in the bulge or halo. Stars that are in the disk are more or less going in nearly circular orbits around. They bob up and down above and below the plane of the disk as they go. These yellow curves here are showing the path of a typical star. Now, for a star like the sun, it takes about 230 million years for it to orbit around the galaxy. And remember, the sun is 4.6 billion years old. And so that means that it has orbited the center of the galaxy about 20 times since it was formed. In some sense, it's kind of like the same age as many of you in the class, about 20 years old, just moving from its teenage years to its 20s, if you think about a year for it as being how long it takes to orbit around the center of the galaxy once. In fact, we'll make that the answer to today's reading quiz. The answer is the sun is 20. The answer to today's reading quiz is the sun is 20. The stars in the halo, they follow these orbits that are like these green arrows here. And the stars in the bulge, they follow the red. And in both cases, those orbits, they're a little bit more random, so to speak. Some may be coming from the back side of the image to the front. Others may be going from the front side to the back. Whereas the stars in the disk, they were all orbiting the same way, counterclockwise, as viewed from this orientation. And so the halo stars have those random orientations, and they also have those orbits that bring them up above and down below the plane of the orbit. So here's a thought question for you. Why is it that the orbits of the stars in the disk bob up and down? Look at these little yellow curves here. Is it A, they're stuck to the interstellar medium? B, the gravity of other stars pull them toward the disk? Or C, the halo stars knock them back into the disk? Go ahead and pause that if you'd like. Okay, so it's not that these stars are stuck to the interstellar medium. It's true that maybe the interstellar medium would supply a little bit of drag on them as it moves through, but for the most part, a star could just kind of pass through the interstellar medium. It's not going to be stopped by it. It's also not that the halo stars knock them back down into the disk. The distance between stars in our galaxy is so great that even though there are a large number of stars, unless the two stars were born together in the same cluster, it's unlikely that you would ever have a collision. Even if I tried to shoot a star up through the halo, the chances of it colliding with some other star are essentially zero, given the drastic distances between stars. The answer here is B, that the gravity of other stars pull the stars back down towards the disk. So look at this little yellow arrow right here. If there is a star up near the peak of that arch, well, yeah, it's still being pulled in more towards the center of the galaxy. That's why it's going on this nearly circular orbit. But there's more mass down below it than there is up above it. And by below, I mean back down toward the disk. And so that pulls it downward a little bit. And then it overshoots and maybe goes below the disk a little bit. And now there's more mass above it, again, back towards the disk. And so then it's pulled back up toward the disk. So remember Kepler's third law. Kepler originally derived that, maybe I shouldn't say derived, he empirically determined it from observations for planets going around the sun. Newton later derived Kepler's third law once he wrote down the universal law of gravity and F equals ma. And that Kepler's third law, as generalized by Newton, can allow us to measure the masses of things. Here, it's going to allow us to measure the mass of the galaxy itself. Remember I mentioned that it takes 230 million years for the sun to orbit around the center of the galaxy once, and that its radius is 28,000 light years away. And so what do we know? We know the orbital period, and we know essentially the semi-major axis of that orbit. And Kepler's third law is that mp squared equals a cubed. If you know p, the period, and a, the semi-major axis, you can calculate m. In this case, m would be the mass of what the sun is orbiting around. And what you find is that within the sun's orbit, you have 10 to the 11, 100 billion solar masses of material. And for the galaxy of a whole, as a whole, the mass is about 10 times larger than that, 10 to the 12 solar masses, or 1,000,000,000,000 solar masses. Now, if you actually look at the light-emitting matter within the galaxy and ask how much mass is in that light-emitting matter, those stars, those gas clouds, and so on, you don't get nearly that amount of mass. You only get about 1/10 of that amount. And what we're learning, or what we've learned, is that the vast majority of mass, not just within our galaxy, but we'll see later in the universe, is of this type that is not light-emitting. And we call this dark matter. Dark matter is named very well. It's matter that is dark. It doesn't emit light. It's a different kind of matter than what we're used to. So we'll be talking more about dark matter as the course progresses. Here in chapter 15, we're going to now discuss galactic recycling. And so the idea here is that you have generations of stars that live and then die and then give their gases back to the surroundings, and then you have another generation and another generation and another generation. And so this figure here from chapter 15 shows the cycle that we're talking about. We'll kind of pick it up here, right, where a star dies and it gives its gas to the surroundings. That gas is going to expand outward in the galaxy above the plane of the disk of the galaxy perhaps, and then fall back down and then form new clouds that form new generations of stars. So let's look at these steps in this star-gas-star cycle more carefully. So we'll pick it up here where stars are dying. Here is a planetary nebula that is putting back its gas into the surrounding space. Remember, when low and intermediate mass stars die, they leave behind a white dwarf, but those outer layers of the star get thrown off into space. And that will put the heavy elements and the other elements, not necessarily just heavy, but all of its elements back out into the surrounding space. Supernovae, they make really heavy elements, even heavier than oxygen on the periodic table, all the way up to iron and beyond. And when they blow up, they put those elements back out into the surroundings. And so the Cygnus loop is what we're looking at here. At the end of this week on Friday, we'll introduce some new constellations, including Cygnus the Swan. And the Cygnus loop is a supernova remnant in the Cygnus constellation. And so here you can see a photograph of that Cygnus loop. Here's a close-up of the filamentary structure you see in that supernova remnant. And if you look at spectra of the Cygnus loop, you see lines that represent ionized oxygen and hydrogen and neon and sulfur and so on. And so there we see that this gas here is consisting of heavier elements. Those heavier elements are going to go back out into the surrounding space and allow to be mixed in with other gases that can then form new generations of stars. Now, in supernovae, remember that the outer regions get shot out at extremely large speeds. And in fact, some charged particles can be accelerated to speeds that become comparable to the speed of light. There are strong magnetic fields that are very dynamically changing in the vicinity of the supernova. You can have those charged particles cycle around the magnetic field lines and produce what's called synchrotron radiation. And so you can look at these supernova remnants in the radio waves as well to learn information about how the material is flowing and where it's distributed. Cosmic rays that we experience all the time from space. These are charged particles that are just bombarding the Earth and swarming through the solar system and the galaxy and the universe as a whole. These charged particles are thought to have originated in these kinds of supernovae events. If you have enough supernovae occur in a region of your galactic disk, then the gas from the outflow can become denser then and poke a hole in the disk, so to speak, and then it gets expanded out in this big bubble on top of the disk. And that bubble will spread out, and then regions within it will start to collapse. And as it spreads out and cools, it'll rain back down onto the disk. And so those cool clouds that condensed out of this bubble fall back down, mix in with the material from the disk, and that can spread that material out throughout. And so the next generation of stars that forms is going to have a higher percentage of metals in it, metals being elements that are heavier than helium on the periodic table, because it's been contaminated or polluted, if you will, by these heavier elements from supernova remnants, supernova explosions. So there are two kinds of gas clouds that we can talk about here. Atomic hydrogen gas clouds, that's when you have H, not H2, not molecular hydrogen, but atomic hydrogen, as the name tells us. And to have atomic hydrogen means you have to have hotter gas. As the gas cools down, then collisions no longer would break apart hydrogen molecules that form. And so for those cooler clouds, those you have H2 in it, we call those molecular clouds. Now, there's a lot of clouds here in the Orion constellation. This great Orion complex shows us that the clouds extend not only down in here near M42, which you learned about, but throughout this whole region. And that is mostly hydrogen molecules throughout that gas. And then there's 28% helium, and then there's trace amounts of heavier elements. So let's go on a fly through of the Orion Nebula, M42. We'll zoom in on that region. And then, of course, this is a visualization. It's not that we've actually sent a satellite 1,500 light years away to fly through the Orion Nebula. But this is what we feel it would look like given the three-dimensional studies that you have. You know how far the individual stars are in this nebula. And so you could imagine flying around and seeing these stars. These are stars that are in the process of forming in many cases, or that have recently formed and have started to radiate away. And their radiation ionizes the surrounding gas. Their stellar winds start to blow away the surrounding gas. So in the Orion Nebula, you have slews of stars that are in the process of forming. You have lots of brown dwarfs as well. Here we're zooming past a proplyd, which is a protoplanetary disk. Here we're zooming on a different one of those. And at the center of this protoplanetary disk, there would be a star that is in the process of forming. And so over time, what would happen is that the solar wind would blow away the surrounding material and be left with the star, a disk of material around it, and these jets that come off. These are called T-Tauri systems when they look like this. The jets are lined up with the rotation axis of this newly forming star. And as we were discussing with proplyds, newly forming stars often have these disks around them. Within those disks, you can have planets that then start to form. So in summary for galactic recycling, stars and planets form out of these coolest gas clouds, these molecular clouds. They'll collapse down, they'll fragment, they'll form stars like I showed you previously with the Matthew Bates simulation. Those stars will start fusion. They'll make new elements, heavier elements on the periodic table. And the dying stars, either through planetary nebula or if high enough mass through supernova explosions, will put their gases back out into the surrounding space. And that will then mix with other gases that haven't yet necessarily been used to make other stars. And those new gas clouds will fragment and collapse down and make a new generation of stars. And each time you go through this process, you will have stars live and die, expel their layers, outer layers, and then get another generation to live and die. With each generation, you're going to, on average, have more and more heavy elements in your stars. So stars in our galaxy tend to form in these nebulae that I've been talking about. And we'll talk now about the different kinds of nebulae, starting with ionization nebula. An ionization nebula is a short-lived nebula around high-mass stars. What's going on there is some stars have just newly formed in this gas cloud, and they are shining light in and throughout the surrounding gas cloud, ionizing the elements within that cloud. And then as the electrons cascade back down onto the atoms, light will get emitted at various wavelengths. And so here we see the spectral signatures of oxygen and neon and hydrogen and other elements. And so these ionization nebulae, they'll look red to the eye, corresponding in large part to the light from falling down onto hydrogen. Reflection nebulae, they'll look blue to the eye. And what's going on there is you have scattering of light from nearby stars. So here, some light from a newly formed star, nice and big and bright, and it comes up this way, and then it scatters off dust in the reflection nebula and then toward our eyes. And so the idea is that the reason that these look blue is the same reason that our sky looks blue, that shorter wavelength light scatters more easily than longer wavelength light. And so the sky is blue because as I look up, not at the sun, but away from it, I'm looking at light from the sun that was blue that scattered down towards me. The red light didn't scatter down towards me because it would have been too big of a scattering angle. It's the blue light that more easily scatters towards me. And the same thing happens in reflection nebulae, that light from nearby stars will scatter within those nebulae toward us, and the blue light scatters more than the other colors. Here's a thought question for you. Because dust scatters blue light more than red, stars seen through a lot of interstellar dust would look bluer than expected for their spectral type or redder than expected for their spectral type. Go ahead and pause this if you need to. Okay, this is analogous to watching the sunset. As you're looking very close to the direction of the sun in the sky, the light coming from it is originally all the colors of the rainbow: red, orange, yellow, green, blue, violet. But the blue light scatters out of the direction towards you and leaves behind the reds and the oranges and the yellow. So if you're looking at that star in the gas cloud and all of its light is coming towards you, it was red to begin with, but there might have been a little bit of blue light mixed in there. Any blue light that there was gets scattered out of the way, gets scattered off in other directions, and makes the star even redder than it was to begin with. And so you got to pay attention to whether you're looking directly at the star or off to the side where the gas cloud is, if you want to think about what color the scattering is going to leave behind. Now, you also have, in addition to these ionization nebulae and reflection nebulae, dark nebulae. A dark nebula is simply a gas cloud where the dust is so dense that it blocks the light from coming through. Perhaps the most famous dark nebula is the Horsehead Nebula. That's what this one is in the Orion molecular cloud complex that we were looking at before. So this Horsehead Nebula is kind of near M42, the Orion Nebula below the belt of Orion, but it's not the same as M42. Those two things are both part of that bigger Orion molecular cloud complex that I mentioned. So if you look at images of disk galaxies, here we see one face on. This is the famous Whirlpool galaxy, and you can see it has spiral arms that are coming out. And those spiral arms have these dusty gas clouds in them. And within those spiral arms, You see red regions. Those are those ionization nebulae we were talking about. And you also see blue stars. Those are young, bright blue stars that have recently formed in the arms of that spiral arm, in the arms of that galaxy. Okay, so we'll say a few words here about material from section 15.3, and we'll be finishing up the chapter on our galaxy next time. And so, in our galaxy, there are two main populations of stars. There are the spheroidal population of stars and the disk population. Now, within the spheroidal population, there are two subcomponents. There's the bulge of stars and the halo of stars. The halo stars, they are older. Many of them are in globular clusters that are 10 billion years old or older. And so, being some of the oldest stars in the galaxy and really in the universe, these globular cluster stars are, they have lower metal abundances. Having been some of the first formed stars, they hadn't yet had their gas clouds from which they formed those gas clouds had not yet been polluted by heavier elements from supernovae and so on, at least not to a significant degree. And so their heavy element abundance is something like 0.02% up to 0.2%, somewhere on the order of 0.1%. As opposed to stars in the disk, those stars, they are all kinds of ages, and they formed from gas clouds that had been contaminated by heavy elements from supernova and explosions. And so those stars, like our sun, typically have about 2% heavier elements in them. We call it the spheroidal population because they're distributed within the bulge or within the halo in a spherical sense. And the disk population, of course, is because they're in this nice flat disk. Now, the last thing that we'll look at today is a visualization of how our galaxy formed. And so we've talked earlier in this course about how our solar system formed, or how planetary systems in general form. And in some sense, it's a similar process, but on a grander, larger scale. That you have a giant gas cloud that collapses down to form the star systems. And then you have many star systems colliding and merging with one another as the galaxy forms. So here you can see a visualization. The dots here are representing stars and star clusters. And there's a lot of dynamic motion going on here. Here we start to see those spiral arms develop. And you can appreciate that there's lots of collisions that occur in the process of these galaxies forming. So that's it for today. I hope you're doing well. Send me an email if you need to talk about anything. We can set up a time also to talk by Google Meet or anything else. Stay safe and take care.